Hi, I'm Professor Angela Rasmussen from the Department of Electrical and Computer Engineering at the University of Utah. And today I wanted to go over a review of circuit analysis when we have a dependent source in the circuit. So here's the circuit that we're going to review. We're going to do this by using node voltage analysis. Remember from node voltage analysis that we have to always define the currents going out of the node we are creating the analysis. So I am going to call this node V1, and I'm going to take the currents going out of here. So going out of here, that would be V1 minus 4V3 over 7K. Again, I always take the plus side of the current and subtract off from the minus side of it. So the first voltage will always be the one that's at the node, or is the plus on that, and then minus any of the other voltages within that next branch. So this current is also going out, but this one has a defined current source in there, but I notice it's opposite, so I use a minus 2 milli. This branch is going to be defined by V1 minus a minus 6 over 5K. And that creates my first equation. So why this is minus is because the minus sign is closest to the node voltage. And so if I was to take a multimeter and put the plus on this side and compare it to the other side, then if this was the plus side and this was the negative side, I am going to measure a minus 6 volts there. So the next thing I want to solve is for I2 and I3. So I2 is located here, and I can describe I2, which I notice is this current, but just opposite. So I2 is going to equal a minus of that. I3 is going to be opposite this current. So I3 is a negative V1, and the minus times the minus gives me a plus 6. For a dependent source, the extra step that you need to take is to define an equation for the variable. In this case, it's V3. So we need to define an equation for V3. I notice that the voltage on this side of V3, if I take a loop from here to this point, that voltage is a plus V1. And then if I was then to continue going through here to this node, I'm going to be a plus 6. And so if I do that, I'm going to have a V1 plus 6 is going to be, and then a plus V3. That's going to get me back to 0. So going across here, back to there, gives me a plus V3 equal to 0. So I could say that V3 is equal to a minus V1 minus 6. So these are my equations. I have 4 of them. I can now write a matrix form and solve this in MATLAB. So to write the matrix, I first need to define the variable order that I'm going to use. So I am going to choose that, and my choice in this case will be V1, V3, I2, and I3. This is an arbitrary choice. I just need to make sure that the variables line up with their values in this matrix. For example, if I look at this first equation, I need to take all the variable coefficients, and that would be for V1, which is my first variable, and that's when I'm going to put this in this location. My second location in the matrix is V3, and so my V3 variable has a minus 4 over 7k. My next variable is I2, and in this case there is no I2 and no I3, but I have a constant value that needs to go over to the right-hand side, and taking that over is going to be 2 milli. My second equation, I need to have all the variables on the same side. So one way of doing that is to get rid of the denominator by multiplying it on both sides, which would give me a 7ki2, and then I can bring over the other variables, and that's going to give me this equation. So my first variable again is V1, and that's a 1 in this case. The next one is V3, which is a 4, and then I have this time a 7k for that I2 variable, no I3, and no constant. I'm going to do the same thing with this equation, so 5k I3, and then I bring over a plus V1, and then equals a minus 6. So I then lump all of the variables together. V1 will be a 1. There's no V3 or I2, and then I have a 5k for I3 and a minus 6 as my constant. This is going to be my last equation, and so I'm going to bring the V1 over to the other side, and I get a plus V1, a plus V3, no I2, no I3, and a minus 6. So from here I can plug this into MATLAB, and I'll make this a little bigger so you can see. So you can see that this will be the same. So my first coefficient, this 1 over 7k plus 1 over 5k, you can notice that I multiplied that out with 1,000 for k. And then I have a minus 4 over 7k as my next variable, or my next spot, and then a 0 and a 0. And then my next row, I have a 1, should I miss a minus sign? I did. So this should be a minus sign here. When I bring this over to the other side, it becomes a plus V1, but it still stays a minus V43, 4V3. And so that becomes a minus 4 from this one. And so there's a minus sign there. And then a 7k, and then a 0. My next row is 1, 0, 0, 5,000. Next row is 1, 1, 0, and a 0. So remember, for the different rows, you use a semicolon. To separate the components, you can do a comma in between each of those. So then I need to define this B matrix. So I called this matrix an A, and then this B matrix is my constant matrix over here. So on my first row, I missed another one. So I missed this constant up here too. So this constant would be a minus was a plus, so that becomes a minus 6 over 5,000. And so that is 2 milli minus 6 over 5,000. My next row is a 0, a minus 6, and a minus 6. And then I can take that x is equal to the INV times A, which just means it inverts that matrix, a to the minus 1. Multiply it by B, and then I'm going to get answers. And those answers are going to be in the same order that I defined my variable order for this vector here. So V1, V3, I2, I3 was that order. And I have the answer from MATLAB, which was here. And so this was my A matrix and my B matrix. Bring this back up. these were the answers just multiplied out. And then this order was V1, so the first variable was V1, the next variable was V2, and then this was I2, and this was I3. So that will give me those answers that I want to solve this problem. Thank you for watching.